here we go. So we're going to change one small thing today, and that is we're going to look at problems where maybe vertical rectangles aren't our best option. Okay, I have a problem that we're going to work through that can be done using vertical rectangles. You can use x values, but there's another way to do it. And that is we're going to use horizontal rectangles. Okay, easy peasy. Okay, so again, representative rectangles, we've done them all where they're vertical and you have a width of dx. Very, very skinny, and then we have an infinite number of them that gets us the area. But now we're going to turn them horizontally where we have a thickness which is dy. There's no question to ask yet.
It's about dx.
I understand. So here are two functions. And you'll notice already they look a little bit different. So instead of being y equals, they're x equals, and then that thing in blue is all wonky. What's that look like, by the way? The red one.
Sideways parabola.
Sideways parabola. What's the blue one look like? Oh, by the way, my viruses are all good.
A different sideways parabola.
Get that. So let's suppose we were given this problem last night on the homework. You would need how many different representative rectangles?
2.
Nope.
3.
3. Okay. One there, and one there. And by the way, the area here is not 0. Okay, remember I talked about this yesterday. You can't, stuff below the x-axis is no longer equal to negative area. Why 3 different rectangles? Well, in this region here, the top and bottom change when we get to that point. So now all of a sudden we get that guy. These are separate regions, so they can't be calculated with one rectangle because we're not including the stuff inside the red parabola. Is it doable that way? Yes, it is. So for instance, the rectangle all the way to the left. Well, that's a little confusing because we'd have to solve for y. When we solve for y, we'd get a plus or minus. So the top part would be the plus part, the bottom part would be the minus part. Subtract the 2 and get a top minus bottom. Do you see where I'm going with this? Okay, it gets ugly. So we're going to use a different approach, and that is we're going to use one horizontal rectangle. That horizontal rectangle will take care of the whole thing. I can start up in this top corner here and work my way down with a different rectangle all the way down to this other point of intersection here. Yes?
Is it safe to say that you could just do it from the top to the origin and just double it?
You could do it that way also, yes, because it is symmetric about the x-axis. Everything we did yesterday is identical except for 2 things. Number 1, instead of working with x's, we're working with y's. And number 2, top minus bottom doesn't work anymore. Now it's going to be right minus left. We get right there, right minus left. So wherever in your notes from yesterday you wrote top minus bottom and put a cloud around it with stars and arrows pointing at it, and highlighted it and did all that other stuff, right below that, put right minus left. Because it's also very important. The concept is identical. Find the area of that rectangle, use the integral as an accumulator to add up all those rectangles. We good so far? When we were working with vertical rectangles, everything was in the form of y equals blah, 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 blah. These should be in the form of x equals blah, 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 which for some reason this one is not, but I think you're all smart enough to realize it would be x equals 2y squared minus 4. So, don't trust the graph. It appears that it intersects at 1, 2, 3, 4, 2. And 1, 2, 3, 4, negative 2, but again, don't trust it. Go ahead and do the algebra, and sure enough, it intersects at plus and minus 2. And again, remember we're working in terms of y, so we want the y values of those points, not the x values. Vertical rectangles, everything in x. Horizontal rectangles, everything in y. Okie doke. How are we doing so far? Oh, look, it matches the graph. Okay. Where did that come from? Well, that's simply right minus left. The right function is the red one, which is y squared, minus the left function, which is the blue one, 2y squared minus 4. Its thickness is dy, so there's the area of the rectangle.
So what is that dy, like what value does that represent?
0.
0?
An infinite number of times. Accumulate. Going from -2 to 2. And as Cam mentioned, we could go from 0 to 2 and double it. We could go from -2 to 0 and double it. Get out your calculators. Now there's a problem. How are you going to fn int it with y's? Well, it's real simple. Just use x's, doesn't matter. You can put little puppies in there and it'll still fn int correctly. So fn int that function, replace the x's with the y's in your formula. Tell me what it is. Because again, like I mentioned yesterday, I'm not so concerned about you being able to do a definite integral, because I think at this point you should be pretty solid on that. What I'm more concerned about is being able to set it up. And we'll go for a consensus here. What do you got, Sid?
On the quiz on Friday, are we gonna have our calculators?
That's a good question. I still haven't figured that out yet. I have to ask my compatriots.
Okay.
Okay.
What?
See, Senor,
I have an answer.
please share.
10.666.
10 and 2/3.
10.
10.666.
Yes.
10.667.
I mean, yeah.
They would, the reason I asked that, not trying to be a smart guy, but the AP will accept rounded and truncated answers. So they would accept both 10.666 and 10.667. You understand the difference between rounding and truncating? Yes or no?
Yeah.
Yeah, okay, good. Can somebody confirm? I don't even know if he's right.
Yeah, he's right.
10.666. Well
What does
done.
the word truncate mean?
Truncate means you just chop off the rest of the numbers.
Okay.
So if you've got .66666, you just lose all the other sixes and stay with what you have. Whereas the rounding rule would be, you would do .667.
Okay.
Most of the time they'll accept either one.
Will it take fractions to like 32/3?
Mm-hmm.
But not mixed like 10 and 2/3, they won't take that.
No, that's bush league. We're done with 1 and 2/3 and all that garbage I get from my freshmen.
We're out of 4/3.
Yeah, exactly. Okay, any problems? How do you know when to do horizontal versus vertical rectangles? Well, sometimes it'll tell you, solve this problem in terms of x, solve this problem in terms of y. Other times when it doesn't tell you, it's up to you. Could I have done this problem the other way? Yes, it's just a lot more work. I've got to solve 3 different integrals and then add all that up, and I should still get 10.666. A lot of it is a convenience thing. Other times you'll see problems where you have to use vertical or horizontal because you have all kinds of problems. So for instance, yesterday in that problem I did with the 2 regions, if I decided to do that using horizontal rectangles, I'd still have to do 2 separate integrals because of the weird points that worked out in that picture.
What does something look like that you're gonna need more than 2 horizontal rectangles?
The one we did yesterday.
You would have needed 2 for that also.
Yeah, because the point of intersection.
Oh, there were 2 different POIs. So you'd have to go one on.
We did vertical yesterday because you had to split it there. If you do it using, vertical yesterday. If you do it using horizontal, you'd have one there, but then you need another one down here because that would be. Okay, so that brings it up another point. So yesterday when we did that problem, we knew we had to do 2 separate integrals because the bottom changed somewhere over the interval. When you're working with horizontal rectangles, if the right or the left changes over the interval, then you need a second integral. Again, changing color because it's important.